Hello. In this video, we'll be talking about how to count different events. And so there are a few rules that we want to understand. The first of them is called the MN rule. If we have an experiment that is performed in two stages with M ways to accomplish the first stage and N ways to accomplish the second stage, then the product MN, there are MN ways to accomplish the experiment. So for an example, if a car can come in one of four exterior colors and one of three interior colors, how many different color styles are the car possible? We can break them down into two stages. And when I do this, I tend to like to write little blanks for the stages to help me count how many things there are. And so if the first exterior color can come in one of four colors, the interior color can come in one of three colors, I multiply them together and I get a total of 12 different color styles for this car that are possible. This rule can be extended. We call this the extended MN rule. And if this experiment, if any experiment can be performed in K stages, so that's just a way of saying we don't know how many stages, there's K. And there are, let's say, N1 ways to accomplish the first stage, N2 ways to accomplish the second stage, and on, and then N sub K ways to accomplish the final Kth stage. Then there is N1 times N2 times ... times NK ways to accomplish the entire experiment. And this is just a long-winded way of saying, if an experiment is performed throughout multiple stages, and I can count each individual stage, then the entire experiment, there's just the product of those ways to do the whole experiment. And so menus are kind of a really easy way to describe that. So for the next example, let's say a menu at a restaurant has, let's say, 4 appetizers, 5 entrees, and 3 desserts, and you want to build a meal choosing one of each. Well, how many meals can you order if one item of each category is selected? And so, this is 3 stages in this case. There's an entree stage, an appetizer stage, and a dessert stage. There are 4 choices for the appetizers, 5 for the entrees, and 3 for the desserts. And we're going to multiply them together, and we're going to get 60 total meal options from this. Those methods work really well if we want to select one item from a list or from a stage. But what if we wanted to count a subset of the number of ways? Like, for example, what if we wanted to select 2 appetizers from that group or 3 desserts from that group, right? There's 5, maybe we have a lazy Saturday or something, and there are 5 movies on Netflix we want to watch, but we only have time to watch 2 of them, right? How many different ways can I select 2 of these movies of the 5 to watch? We're selecting a subset. And we need new counting rules. And the first one we have is what we call a counting rule for permutations, right? And a permutation is just an arrangement, so an ordering of n distinct objects, taking r of them at a time. So if we want to count the number of ways we can arrange in order n objects, only taking r of them, we use the notation n permute r or NPR, and that formula is n factorial over n minus r quantity factorial. And we may be familiar with this exclamation point or factorial notation. And all it means is the product of everything from that number n all the way down n minus 2 times 3 times 2 times 1, just the product of all the numbers. To make some of this work, we need to define one thing. We define 0 factorial to be 1. And there is kind of one thing that's nice to notice about these things. There is kind of a pattern that fits with these factorials, right? So if we have n factorial over n minus r factorial, one thing we should notice is since n is the product of all the integers from n all the way down to 1, and the same thing with n minus r, it's the product of all the integers n minus r all the way down to 1. What we should see is right here and on is all of the factors in the bottom. So they, in a sense, can cancel each other out. And all that we're left with is the factorials, is the factors that are larger than our denominator value, n minus r. So for example, if we looked at 5 factorial over 3 factorial, and we wrote this all out, this would be 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1, right? What we should notice is that 3 times 2 times 1 will get there, and we're just left with 5 times 4. If we had 7 factorial over 2 factorial, right, we would get 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1, and those would cancel, and we just get the product of 7 times 6 times 5 times 4 times 3. So we can use that shortcut when we're computing these factorials. For example, if I had 6 factorial over 4 factorial, I can say right away, I see the pattern, and this is just going to be 6 times 5, which then would be just 30. Let's do an example of this. So we might want to know, for example, how many ways can 12 runners in a race be awarded first place, second place, and third place? Right? In this case, I have a total of 12 people that we're trying to arrange, right? And in this situation, finishing in first place is different than second place, is different than third place. So we're definitely talking about an ordering. And in this instance, we're talking about an ordering of 3 people, right? I want to order these 12 runners in just a subset of 3. So if I want to count this using permutations, we would say this is 12p3 or 12 permute 3, which in the formula would be 12 factorial over 12 minus 3 quantity factorial, or 12 factorial over 9 factorial, right? Eventually, we might be able to skip this step and just know that this denominator is going to be the difference between these two numbers and just go right to 12 factorial divided by 9 factorial, and that would be fine, right? If we remember the shortcut for canceling out factorials, I know that in here, I'm eventually going to have a 9 factorial that will cancel. The only things that will be left is every factor that is bigger than 9. So that means it's 12 times 11 times 10, right? The next integer would be 9. That's going to cancel with everything in the 9 factorial. This, if I multiply this out, is going to be 1,320 different arrangements of these 12 runners. This permutation rule, and then the last rule we're going to come up with called the rule for combinations, are just tools that are supposed to help make counting a little bit easier. We don't always need to employ them, right? Sometimes the MN rule or extended MN rule is fine. So let's look at this example, right? A 3-digit password is created from selecting one alphanumeric character. And again, alphanumeric is just going to be a letter or a number from 0 to 1. And so if we want to select one of these characters from 3 for each 3 digits, how many different passwords are there? We can really use the extended MN rule here and think about this going over 3 different stages. The first stage being selecting the first digit, the second digit, and then the third digit. If we're allowed to select an alphanumeric character, there are 26 letters, and 10 numbers to select from. So a total of 36 for the first one. If I look at the second one, the second stage, if there's no mention about uniqueness, we can assume we can reuse the characters. So for example, we could have a password that's like AA10, or I'm sorry, AA9, right? We're allowed to kind of do that if it's not stated that these characters must be unique. Then there are 36 choices for the second one, and again, 36 choices for the third one. I want to multiply them together, and I get 46,656 possible different passwords. If I look at the second example, we're building a 3-digit password created from selecting unique alphanumeric characters. I can still use the extended MN rule. right? There really is, even though we have the permutations, I can still think about this way if it's easier to think about it using uh, kind of developing over stages. When I look at the first digit of my passcode, there's still 36 options. When I look at the second digit of my password, it's because I want a unique character, I now only have 35 options to pick from because I would have picked one for my first digit, and then I would have had 34 for my final digit in my 3-digit password. And if I multiply these together, like the extended MN rule says we should do, this is 42,840, right? So just because we have things like permutation rules or what we're going to do when we talk about combinations now, we don't always have to use them, right? Kind of inherent in every example we do is having to kind of think a little bit critically and say, do I need permutations? Do I need combinations? Or can I just get by with using the extended MN rule? Or do I have to use a kind of a mix of them, as we'll see? So let's move on to the combination rule. And so what if I want to select a subset of n distinct objects, but I don't care about the order. I just care that I've selected them. And the word we use for this is like committees, right? Or a team. It all that matters is you're on the team. It doesn't matter, what if you were picked first or second or third in this case. It just matters that you're on the committee. Combinations are kind of like the participation trophy of counting, right? It just matters that you're there. So the number of distinct combinations, right, where we don't care about the order of n distinct objects, taking r at a time, is what we call n choose r or NCR, and it's very close to the permutation one. It's n factorial. This time we divide by r factorial and n minus r factorial. There is an alternate notation we might see, and it's this kind of parenthetical notation. I'll make that parentheses a little bit better. That notation is called a binomial coefficient. We don't really need to worry about why it's called this. However, this might show up maybe in a homework problem, maybe on one of the exams or whatever. We just want to understand that these two notations mean the same thing. They mean n choose r. Then I'm going to take n factorial divided by r factorial, n minus r factorial. So let's do kind of two examples that take this into account. So the first one, a 5-person committee is to be formed from a cohort of 12. How many distinct committees are there, right? And in this case, the order that I have, that I'm selected from this committee, does not matter. All that matters is someone is selected from the committee. So there's a total of 12 people to select. We want to select 5 of them. So this is going to be 12 choose 5. And the formula, this would be 12 factorial all over 5 factorial, 12 minus 5 quantity factorial, or 12 factorial, 5 factorial, and then 12 minus 5 is 7 factorial. And now to actually compute this, we use the same strategy we did before, which is when I look at my denominator, right, because the 7 factorial is larger, I know that it's going to cancel more terms of my 12 factorial. And so what I can do is I can list all of those factors of 12 factorial that come before 7. Right? Everything after that 7 is going to be canceled out by the 7 factorial. But with combinations, that's not the end of the story. I still have this 5 factorial I haven't done anything with. And so I just list it down. And what we can do now is just start to reduce. Right? 5 and 2 cancel out with a 10. 4 and 3 cancel out with that 12. And so now we're left with just 11 times 9 times 8. And if we compute this, this is going to be 792 possible different committees. Right? What is nice about combinations is the solution to a combination will always be an integer. Right? It will always be the case that even though 12 and 5 don't reduce at all, when we look at their factorials, we're always going to get kind of this perfect reduction like this, that every factor in the denominator will eventually be canceled by some or multiple factors in the numerator. And then we'll be left with some kind of subset of these numbers, in this case, 11, 9, and 8. All right, let's look at our last example. This is going to take kind of everything together. So maybe a wedding venue has 12 appetizers, 5 entrees, and 4 desserts. And this venue, a menu, if any of you have been to a wedding recently, you know that you don't always just have one appetizer there. There might be 4 or 5 appetizers that the couple pick out. Or they might be 2 or 3 entrees for you to select from when you reply. And then they might have 2 or 3 desserts on a dessert table. So now we're not just picking one from each category, we're picking a subset from each of these categories. So a menu for this venue consists of selecting 4 of the 12 appetizers, 2 of the 5 entrees, and 2 of the 4 desserts. How many different menus are possible? And so this is going to be a mixed approach. We're going to use the general or extended MN rule with combinations. All right? Why would we use combinations and not permutations? And the answer is, when we're selecting a menu, does it matter which appetizer of the 12 is picked first, or does it matter just that you're selecting an appetizer? Because it's the latter, that's what we're going to go with. So the way we use the extended MN rule is for each of these 3 stages, right? The appetizer stage, the entree stage, and the dessert stage, we can separate them out. And then each of these stages, we can count how many ways there are to select 4 appetizers from 12 entrees. There are 12, choose 4 ways to do that. How many ways are there to select 2 entrees from the 5? There's 5, choose 2 ways to do that. And then 4, choose 2 ways to select 2 of the 4 desserts. And the extended MN rule says all we have to do is multiply these things together. And we can do that down here, 12 factorial over 4 factorial. And I'll skip 12 minus 4, that's 8, times 5 factorial over 2 factorial, 3 factorial, 4 factorial over 2 factorial, 2 factorial. And if we do this, if we compute this, we'll kind of save some time with the computation. We could go through that, but if we do it, we get 495. If we computed 5 factorial divided by 2 factorial, 3 factorial, we would end up getting 10. And then 4 factorial divided by 2 factorial, 2 factorial, that would end up being 6, to getting a grand total of 29,700 different possible menu options using this. Okay, hopefully this was helpful. If you have any questions, let me know. If not, I'll talk to you next time.